All right, so here's what we were talking about last time. It was directional derivatives. And reminder, here's our definition. Directional derivative, denoted like this, is computed by this formula. The motivation, of course, is, look, dot product with the gradient from the previous page, dot product with the gradient, we've already seen, turns input changes into output changes. So it's pretty naturally motivated, right? Notice that's all we're doing. We're taking whatever is the input change vector indicated in the notation for the directional derivative, and we are literally dotting it with the gradient, right? So the weird thing to keep in mind is that in this book and in others, and depending on who you talk to, but for the purposes of this course, the word directional derivative requires that input vector be a unit vector motivated by the direction that is part of the term directional derivative. Okay. All righty. So we talked about some points of view on this last time. A couple of the big applications. Directional derivatives compute this very natural quantity, df/ds. Right? You're keeping track of the values of some function f as you move around in the domain. How much does it change per unit distance traveled? An extremely natural thing to want to talk about. And we motivated why that's true. It's a matter of breaking down a velocity into a unit direction, a unit vector direction, and a speed, and computing accordingly. And there it is. Nice punchline from that is that means that directional derivatives are slopes of graphs, right? Another natural thing. I mean, well, okay, mostly natural thing. Now, again, this is peculiar to graphs. Cannot emphasize that enough, right? This is a peculiarity of the graph construction. But we look at graphs sometimes, if not often, right? So, pretty cool. All right, and that's where we left off last time. I want to show you how you can use directional derivatives in computations sometimes. Here's a scenario. Suppose we're keeping track of the temperature as a function of location in some three-dimensional context. And we're moving on a path that's parameterized path. So, okay. And the question asks, how would you compute dTds? Now be careful of the idea of just plugging the parameterization into the temperature function and taking the derivative of that as written, because that would compute the rate of change of temperature with respect to time, which is not what we asked, right? We've asked for the derivative with respect to distance traveled. Okay. So one thing you could do is reparameterize that curve. You could reparameterize in terms of distance. Right? The book actually shows you how to do this in section 12.6. It's not that big of a deal, but there's a component of tedium to it, and it's good to be avoided if we can, and good news, we can. If we want to compute dTds, all we have to do is compute the directional derivative. Right? Directional derivative. Namely, find a unit vector pointing in the direction that we want to go. That unit vector is easy to compute, right? We just take our velocity. Velocity is a tangent vector to the curve. Velocity points in the direction that we want to go. We need it to be a unit vector, though, so we don't write down the velocity. We write velocity divided by speed. Right? There's our unit vector pointing in the right direction. And the way you compute the directional derivative is with a dot product with the gradient. Right? So pretty straightforward. Nice computation. Alternatively, you could, I suppose, also instead write dt ds is equal to dt dt divided by ds dt. Right, now that's sort of a single variable move right there, single variable chain rule. That everything works out, the single variable chain rule. And then just notice that ds dt is speed, and again, I already know how to compute speed. So you can see there in the same, it's really kind of the same deal. We're just dividing the time derivative by speed. So it's an equivalent calculation. But anyway, your preference. Okay. All right. Next question. Suppose we want to compute derivative with respect to time. Okay, yeah, sure. And so you could, use the chain rule to do that. I'm just going to point out another option you could instead do is here's that single variable chain rule trick again, and then notice that the dTds, which is a directional derivative, because the direction we're going is not just a unit vector, well, the direction is a standard basis vector. In this case, that directional derivative turns into a partial derivative. World's easiest derivative to calculate. And that's kind of a cute trick, right? I mean, nice. We're all, I don't want to say lazy, but there's an aspect of lazy. We're all interested in the idea of saving effort, right? There's nothing wrong with that. And this is kind of a slick way of avoiding a little bit of effort, maybe. So that's nice. Okay. Right. So I do want to point out, though, that you shouldn't really think of the directional derivative as a construction, as something that's there as a computational tool, because it really isn't. Don't think of the directional derivative as computation, even for what we've seen so far. I mean, here, maybe we saved ourselves a little effort. Here, maybe we saved ourselves a little effort, but not much, really, in these cases. Right? The main reason that you need to understand directional derivatives is not because it's a computational tool. Usually it's not. Right? The reason you need to understand directional derivatives is because it is the thing that naturally connects to certain kinds of applications that we want. So, for example, sometimes you really want to know the slope of a graph. Well, the directional derivative does that. Right? So you need that as a concept in order to connect to something that you want to be able to talk about. Likewise, df/ds. This is natural, important, right? And so that's a motivation for wanting to understand directional derivatives. Okay. Just to emphasize how directional derivatives are not computationally really a big win. Here's just a for example. Suppose you've got some velocity vector given and you want to compute, how does some function capital T change with respect to time? Sometimes we want to know that too, right? So look, here's how the directional derivative calculation goes, right? I want to know this. Directional derivatives are that. So I have to start off by relating with this equation, the single variable chain rule, to kind of connect these two different kinds of derivatives. ds dt, of course I know, is speed, namely the magnitude of the velocity vector. How do I compute the directional derivative here? Well, dot product of the gradient with the unit vector. Well, okay, the unit vector pointing in the direction of a given velocity vector is, well, you divide the velocity by its magnitude. Okay, so there's how that calculation goes down, and then plug and chug. On the other hand, check it out, single variable chain rule. You want to know dt dt? Good. Compute by dotting with the gradient. Dot input velocity with the gradient to get output velocity. Super, extremely natural. Right? And compare the results, by the way. This is where I think it gets even kind of funny. If you compare these two calculations here, computing this versus computing this, the difference is that doing it the directional derivative way, I'm computing the speed and then both multiplying and dividing by it. Right? I mean, what's the point? It almost makes this first calculation look a little silly. Okay, so as a computational tool, the directional derivative it's not important. It's not a big deal. It's as a conceptual tool that it's interesting and important. Okay, everybody good? All right. Okay, moving along. We're talking about gradient vectors. Now, I know we've talked about gradient vectors before. We've been using gradient vectors as a computational tool, right? It's a It's a nice shorthand to represent all the partial derivatives, which we need to be able to represent because that's what's used in the chain rule. This is how we use the chain rule to relate input changes to output changes. So it turns out, though, that the gradient vector also has some nice geometric features, geometric connections. So that's what we're going to talk about now. The first one of these comes about by asking this, I think, very reasonable question, which is, suppose you have a scenario like this where you have a function from R2 to R1, for no particular reason. And I am at a certain point here in the domain, and thus my output value has a certain point in the target. And reasonable question, look, I could start moving in various different directions from where I am. I know that for each direction that I move in the domain, there's going to be a corresponding movement in the target. Right? And which of these directions, we reasonably ask, makes the function increase the fastest? Right? Now, that's a very natural thing to want to do, right? Maybe that point represents where you are in the map and you're cold. And F is temperature. Well, you want to move in such a way that the temperature increases as fast as possible, so you warm up as fast as possible. Right? I mean, that's just physically relatable. Now, on the other hand, maybe this point over here represents a collection of parameters describing the current state of a mechanical system that you're tinkering with. Or maybe it represents the current state of your small business and you're trying to increase profit as fast as possible. Right? There's lots of examples of situations where you've got a function, you're looking at a point, and you want that function to increase. Right? Or decrease. Maybe that's where you are in the map and you want temperature to decrease because you're hot. Right? How would you make a function decrease as fast as possible? I'm not going to spend any real time talking about that because just notice if you want F to decrease as fast as possible, that's the same as wanting negative F to increase as fast as possible. So let's focus on the increase as fast as possible, and then if you want to decrease, throw in a minus sign. It's not a hard adaptation. Okay, so we're going to consider all unit vectors from this point representing directions in which I might go. By the way, why unit vectors? Right? I mean, why don't we talk about all vectors? And the reason why is you could certainly imagine, at least in a lot of situations, that how fast you move in the whatever the optimal direction is maybe that's already set. Maybe that's already fixed. Look, I can only run so fast. And the rate at which I can run north is pretty much the same as the rate at which I can run south, which is pretty much the same as the rate I can run in any direction. So let's not talk about the rate. Let's just talk about directions, right? Right. So unit vectors are a natural way to focus again just on directions. Okay. All right. So of all these unit vectors, which one maximizes the directional derivative? Well, easy calculation as it turns out. This directional derivative we compute with a dot product with the gradient vector, right? These unit vectors that I'm looking at will dot with the gradient. Good news, I know how to compute dot products. There's an old formula from chapter 12 for how to compute dot products. Right? So I want to make this expression here as big as possible. Don't forget, u is a unit vector, and so that means that this whole factor right here is just a great big factor of 1, magnitude of a unit vector. So let's get rid of that. Right? So the thing that I want to maximize, there's a formula for it. How do we maximize this thing? Okay. Where's the gradient vector on this picture? I haven't drawn the gradient vector on this picture. So let me do that just to keep us going along here. So let's say that's the gradient of f. Right? There's the gradient of f, and I'm considering of all these possible unit vectors. As I consider different unit vectors in all different directions, what happens, blah, blah, blah. Well, notice, as I consider different unit vectors, the gradient vector isn't changing. The gradient vector only depends on where we're at. And we haven't answered the question of which way we're going yet, so we haven't really started moving yet. We're at the same point, considering all these different unit vectors. So the gradient vector is fixed. So this thing right here, the magnitude of the gradient vector, this is a great big constant. So, okay, now, all things together then, how do I maximize the directional derivative? Well, maximize cosine theta. And that's all it comes down to. How do you maximize cosine of theta? Keeping in mind theta is the angle between. Let me just switch over to. Let's see here. What would be a good color here? Orange, fine. The angle between these two vectors. The angle between gradient of f and u. So, for example, if we're looking at that unit vector, theta is that. Well, algebraically, super easy. You maximize cosine theta when theta is 0. If this angle theta is 0, what that means is the correct unit vector to pick is the one whose angle with the gradient is 0. Let me say that a little bit differently. The correct unit vector to pick is the one that points exactly the same direction that the gradient does. Because if it's pointing in the same direction as the gradient, then that angle would be 0, and then cosine theta is as big as it could possibly get. And so, thus, here. So, the ideal unit vector is the one that points the same direction as the gradient. And so, here's a formula for it. Unit vector pointing in the direction of a given vector, bam. Everybody good? So, this is actually an interesting feature of the gradient vector. And this is a geometric feature of the gradient vector. The direction that it points, now, that's intrinsically geometric. That's a geometric thing, right? The direction that it points is the direction that maximizes the directional derivative. So, cool. All right. Alrighty. So now let's ask the natural next question, which is, okay, cool. So I'm moving in the direction of the gradient vector. That being given, as I move in that direction, what is that directional derivative? This thing that I'm trying to maximize. If you're trying to maximize something, and if you figured out how to maximize it, you're going to want to know, how well did I do? What is that maximum that I just achieved? Well, you're going to take that unit vector direction that you're moving. You're going to plug it in. Right? And then, then here I have a little bit of algebra, gradient divided by its magnitude. I could rewrite this as, you'll notice, gradient divided by magnitude. And this is magnitude squared. So I have magnitude squared divided by magnitude, and that gives me magnitude. So, weirdly, check it out. The gradient has again ended up being the answer. Let me say that a little bit differently. The geometric feature of the gradient, namely magnitude. Right? A geometric feature of the gradient has ended up being the answer to a reasonably interesting question. How fast is it increasing in its optimal direction? So this is a couple of nice features of the gradient vector that we've never seen before, and I like to phrase them as a couple of statements instead of as a couple of answers to questions. But this is what I call a geometric characterization of the gradient, which we've never had before. Up to now, the gradient has been, an ordered n-tuple consisting of all the partial derivatives thought of as a vector so that we can do dot products, but ultimately whose purpose is to help us do algebra of computing the chain rule. Right? So it's been a very algebraic tool up to now. Now here's a geometric way to say it. It's the unique vector in the domain whose direction is the direction of fastest increase and whose magnitude is the rate of change or slope or whatever you want to call it in that direction. It's a very natural, geometrically conceived vector. Okay, a little bit of terminology. Direction of fastest increase. I think it's a very simple and natural terminology to motivate, right? That's, after all, what it is. It's the direction in which the function is increasing the fastest. That's how we thought of it, right? But people have this attachment to graphs. And so let me point out, yes, it is true. If you are looking at a graph, then the increasing of the function, if you're looking at a graph, the value of the function is up. That means you're going up on the graph as fast as possible. And so sometimes they call this the direction of steepest ascent. And okay, I guess you can do that, but that makes sense only, exclusively in the graph context. And this direction of fastest increase, that makes sense in any context, including the graph context. This makes sense all the time. So I am a big believer in this term. I have a strong preference for it. That said, this term here is very common. And so you're welcome to use either, but I think you'll find it's ultimately more helpful to understanding the idea if you focus on this term right here. Okay. All right. So, moving along. Here's another neat thing about gradients. Gradients are always orthogonal to level sets of the function whose gradient you're talking about. So now this is a geometric statement. Again, geometric because of the orthogonality, right? So this is a geometric feature of the gradient that we have not seen before. Level sets, right? Geometrically pretty natural. So being geometrically related to something that's geometrically natural, that's a geometric property of the gradient. Okay. It's not hard to see why this is true either. So let's look at this scenario here where I have a function from Rn to R1. Now I'm going to draw just the domain here. So this is just the domain. So this is not a graph. Don't think graph. This is absolutely not a graph. Right? Just a domain. So the function f is like this. There's then there's some target axis over here, but we're not going to be thinking about the target. So just looking within the domain. Here's what a level set looks like. And a level set, of course, is described by the function being a constant. Let me say that a little bit differently. The function being constant means the function isn't changing. Right? That's another way to say constant. The function isn't changing. And so, wherever we might happen to be, if we are sitting, for example, at this point on the level set, if we move tangent to the level set, in other words, if we're moving along the level set, whichever direction we go along the level set, any of these directions, dx, tangent to the level set, the function's not changing. So df is equal to 0. Yes, but don't forget we have a formula for how to compute df. You can think of this as the chain rule or the whatever your preference. Right? But df is computed with a dot product with a gradient. And so when we say the function isn't changing, df is 0, that means that this is 0. That means, now let's just take a geometric interpretation of this statement down here. Geometrically, this says the gradient vector, by virtue of dot products being 0, the gradient vector is orthogonal to all of these tangent vectors dx. All of these purple dx vectors. Gradient's perpendicular to all of them. Now, how could that be? How could a gradient vector be perpendicular to all of the tangent vectors? Well, it can only be perpendicular to all of the tangent vectors if the gradient vector itself, where am I going to put it? There we go. If the gradient vector itself is perpendicular to the surface, like I have here. Yeah. So, another neat fact. By the way, a long time ago, I made the observation that we're gonna see in this course various connections between different types of pictures with calculus. And so here is a pretty good one. This is an example of what I'll call the calculus of level sets. Right? So it is specifically because this is a level set and not a graph, a level set specifically, right? That I can talk about, oh, well, here's a calculus fact that relates to it, right? The gradient vector, that's a calculus thing. It's made up out of derivatives. It is a kind of a derivative on its own, right? It relates input changes to output changes. That calculus object relates to level sets in a certain way. So here's some calculus of level sets. Right? Partial derivatives. Maybe the easiest way to visualize partial derivatives is as slopes of tangent lines to graphs. So you might think of partial derivatives, and certainly that interpretation of partial derivatives that's calculus of graphs, right? Okay, so remember, I made this statement a long time ago that the reason you have to be really uptight and careful about the difference between graphs and level sets and, look, wait a minute, I just need to know what kind of a picture am I looking at here, is because calculus looks different on all of them. And it really does. So we're starting to see that now. Right? This picture of gradients are perpendicular to level sets is calculus of level sets, not graphs. Okay. All right. And there's a nice application specifically of that point, so this makes it for a good segue. Let's talk about the tangent plane to a graph. We've already done this, right? We took a partial derivatives point of view on finding a tangent plane to the graph, and the argument that we made was, well, let's find a linear approximation, L, from R2 to R1. Right, the linear approximation mimics f. It mimics f in terms of partial derivatives and values, but also partial derivatives, right? And then we look at the graph of the level set, L, oh my God, the graph of the linear approximation, right? And we made the argument that because this function approximates that function, stands to reason we should expect this graph to be tangent to that graph. And this, of course, is the equation of a plane, and we call this, therefore, the tangent plane. And more details, of course, on that back when we were doing partial derivatives. Okay, so that's one point of view that you can take, and that's fine, and nothing wrong with it. Make sure you understand that point of view. But I'm going to show you a different point of view on how to motivate the equation of a tangent plane. I think this one's lovely. It goes like this. We're looking at a graph, sure. Oh, let me switch to highlight. We're looking at a graph, but remember we had this trick that we saw back in chapter 12, early chapter 13. If you're looking at a graph, it's written as an equation, but you can toss terms around to other sides of equations and make other equations. In particular, you could rewrite this equation as z minus f of x comma y equals 0, and written like that, this equation, namely that equation, but let's focus on it being this equation, this is the g equals 0 level set of that new function. Now that's an old, right, that little algebraic trick right there is old news. We did that weeks ago, right? But now we've changed a question that was originally given as, I want to look at the tangent plane to a graph. We've now reinterpreted that as I would like to find the tangent plane to a level set. Tangent plane to a level set. Oh, well, look, tangent plane to a level set, here it is. Right, there's a tangent plane to a level set, and I already have a normal vector, the gradient. It says right there, the gradient's perpendicular to that plane. That's what a normal vector is supposed to be. So all you have to do is use the gradient vector as your normal vector. You've already got a point sitting right here, right? Remember, we were looking at, let me switch to a pencil. We were looking at like an A comma B down there. So that means this point here is A comma B comma f of AB. Okay. Got ourselves a normal vector in the form of the gradient, and n dot x equals n dot x naught. And bam, we're done. It's super fast, and here's those details. Excuse me. So here's our normal vector. We're just going to use the gradient. Now, I emphasize the gradient of the function whose level set we're looking at, right? And now that's right here on this picture. It's the gradient of the function whose level set I'm looking at. Right? So now in this context over here, what function is it whose level set I'm looking at? Well, I'm looking at the level set of g. Right? So specifically, it's the gradient of this function g. And so take the various partials. Now, careful though, we've got 3 input variables, x, y, and z. Right? So x partial, y partial, z partial. Don't forget that z partial. It's a function of 3 variables. Right? It better be a function of 3 variables. We need that normal vector to have 3 components. It is, after all, a vector in R3. Okay. So there's your normal vector. Here's your x naught, and plug it on in. And it's all over but the shouting. I'm going to let you all read through the algebra. This is a healthy exercise to plug in that algebra and work it on out. But you plug in this normal vector and this x naught and the equation of the plane becomes this very familiar final answer that we already knew was the answer anyway. We better get the same answer. We're, 2 different solutions to the same problem had better get the same answer. And so good news, we get the same answer for the equation of the tangent plane. The familiar result of it being the graph of the linear approximation. Okay, so I think that's a really cool calculation. Here you might say, and I think this is a nice way to think about it, here we used the calculus of level sets instead of, we sort of pivoted away from the graph point of view and decided to change this into a level set point of view, and we used the calculus of level sets to answer the question. Okay, so great. So we're done with that section of the book now. We're going to move along and go into chapter 14 now. Let me recognize I am skipping a few sections in chapter 13. So all the optimization stuff in chapter 13, that's 13.5, 13.9, and 13.10. I like to do that at the end of the course. Roughly speaking, because chapter 15 is very challenging. Chapter 15 is best done as soon as possible. Tragically, chapter 15 requires most of the course as prerequisite, and so I can't just start with chapter 15 on day 1. It wouldn't make a lick of sense, right? Not at all. So, but anything that's not prerequisite to chapter 15, I like to delay until last possible second. And the optimization stuff in chapter 13 is pretty much the only thing that's not prerequisite to chapter 15. So anyway, it's not prerequisite to chapter 15, so I delay it until after chapter 15. That means we'll get done with chapter 15 earlier. That means you'll have more time to let the chapter 15 ideas soak in, sink in. You just have more time to kind of like let that grease get into the gears and just start to make sense for you. Right? And I think that's super valuable, so that's why I do that. But anyway, we'll cover all that optimization material, 13.5, 13.9, 13.10, later. Okay, so starting chapter 14. Integrals. First, I want to talk about what an integral is. Single variable calculus. I know you all know single variable calculus, right? It's a prerequisite to this course. But it's just so common that students have a foundational perspective on integrals that's kind of wrong, and certainly problematic in a multivariable calculus course. And that is, a lot of students have this mistaken belief that ultimately, deep down, fundamentally, the way to think about integrals is that they are the area under a curve. And that is a pretty, I mean, I know everybody here is like, wait, is that wrong? I thought that's what an integral was. You're telling me that's not right? Yes, I'm telling you that's not right. It is a true statement that integrals compute area under curves, or appropriately nice curves. But that's not the fundamental way to think about them. That's certainly not the definition of an integral. And it is actually a problem if you were to use area under a curve, under a graph. There are graphs again. As your definition of an integral. It's a big problem. Now, there's a long discussion as to why it's a problem. I don't have time to go into that here. It's like I say, it's prerequisite to this course, but at the same time, I know it's not usually made as big a deal out of in Calc 2 courses as I like to make out of it here. So this is one of the topics for which I have a recording on my YouTube channel in the miscellaneous topics section. The title of the recording is "What is an Integral?" It's about a half an hour. Near the end of the video, I get off and talking about infinitesimals, and you don't need to watch that if you don't want to, although I think that's another nice little myth that should be dispelled, as I really encourage everyone to watch the whole video. But certainly, most of the video is important and will address the question of why do we need Riemann sums, what's the point, and what's wrong with thinking about integrals as area. So if you're not 100% clear on the answer to that question, please watch that YouTube video. Again, it's in the miscellaneous topics playlist. So, short version, here's why we need Riemann sums. It's because there are tons and tons of applications. Tons, I mean bazillions of applications of integrals that work like this. That application, whatever it might be, I can write the answer to the question as a Riemann sum. Mass of a one-dimensional rod, the amount of work that it takes to perform a certain task, the number of bacteria in a petri dish, whatever it might be. Riemann sum is how you can get your hands on the question, right? And so a lot of you might be thinking, but wait a minute, I can do that with area too. And I talk about this in the video, but short answer, not really, not without the idea of a Riemann sum. Any perspective that you might have on how you can think of, for example, the mass of a rod. I guess I don't have one drawn here, but the old mass of a rod example in Calc 2 classes. Here's your x-axis, and here's your metal rod of non-constant density. If you want to think of that as area, which notice it's certainly not written as area. Where's area in that picture? I'm not computing the area of that rod, right? If you want to think of that as area, you have to sort of choose to draw such a picture and then argue that the computation of the area is morally equivalent to the computation of the mass. And the way you make that argument, that those two computations are the same, is with Riemann sums. So you're not avoiding Riemann sums at all. You're just unnecessarily bringing a second question into the mix that actually serves no purpose. Okay, more details in the lecture. Anyway, it's really important. Make sure to watch that. Okay, so fundamentally, we solve problems, applications, by writing the answers to those questions as Riemann sums. That's why it's important that integrals be defined as Riemann sums, and that's why, by the way, the fundamental theorem of calculus is so valuable, right? You know how people talk about the fundamental theorem of calculus as being a big deal? It's not because it's just all that important in the real world to compute areas. Like, we're just constantly dealing with areas. What's the area of that thing? What's the area of that thing? What's the area of that thing? Oh my gosh, so many areas to compute. That's not what's going on. It's actually I don't want to say rare, but it's not very common that you really fundamentally, I really need to know the area of that thing. It doesn't come up very much, right? The reason that the fundamental theorem of calculus is so important in applications for engineers and economists and biologists, other kinds of scientists, is because the fundamental theorem of calculus allows us to compute Riemann sums. That's why it's important. And the reason that we care about Riemann sums is because that's what connects to applications. Okay. All right, so I've just... well, anyway, so that's that's a very brief summary of that YouTube video. Okay. So Riemann sums are important. Just a reminder what a Riemann sum is. Here it is. That's a Riemann sum with, don't forget these little details that go into what these things are. But so this should all be review, Calc 1, end of Calc 1, start of Calc 2. Make sure that you're really solid with this. I know that in a lot of high schools, they present Riemann sums as the sort of, oh, well, that was the old way of doing things, and then Newton came along and found the fundamental theorem of calculus, and now, who would ever do that ever again? Wrong. Absolutely wrong. Side note, Riemann wasn't even born yet when Newton came up with calculus, so this is not outdated anything for your consideration. Okay, so make sure you're good with Riemann sums. Let me point to some things about Riemann sums that are, I think, important. Y'all already know these things, I hope and assume. First, we're going to take our domain and chop it up into little pieces. Here are the sort of the specs of chopping up the domain into little pieces. On each little piece of our domain, we're going to multiply the value of some function, depending on what application we're interested in, times the size of that little piece, which of course is delta x. We're then going to take all those little calculations on each piece. We're going to add up over all the pieces. And then, having added up over all the pieces, we have to recognize, well, we chopped them up into little pieces, but they still have some size. There was still a certain amount of a rounding error involved, and these are, in fact, just approximations. And so, but hopefully if we take the limit as the number of slices goes to infinity, then hopefully those round-off errors will go away. And for a very large category of cases, they do. And that's not what this course is about, but anyway. Okay, so that's roughly what's going on in a Riemann sum. The reason that I am breaking this down in this way for you is because, let me just remind you, we are now in a multivariable calculus course, and so we want to write down the definition of an integral in a multivariable context. We want to do a multivariable integral. And before we can write down a reasonable choice of what a multivariable integral ought to be, we kind of have to ask the question, well, what are we generalizing? Right? I mean, we're trying to generalize a single variable concept. Generalizing means take the base version, retain the sort of the high level characteristics, find some low level specifics that are peculiarities of your original context, and just lose those low level specifics that are peculiarities of your original context. Right? So in this situation, what is it that is really fundamentally about what a Riemann sum really ought to be? And what is it about this that is, well, just, a peculiarity of the fact that we're doing single variable calculus? And so here's what I propose, and that is that what we've got here, this is all to be kept. This is all fundamental to what a Riemann sum really is. And honestly, the specifics, the peculiarities that are associated to this being a single variable Riemann sum are just kind of these details right here. It's the fact that size is length. Right? If you're in a one-dimensional context and you ask how big something is, nobody could possibly have meant volume. Right? There is no volume. You're in a one-dimensional context. Size means length, and length is computed with a formula like that. Okay. So what we're going to do is we're going to take all of this business and we're going to try to ask, what would it look like if I did all of this, but now in a two-dimensional context with a two-dimensional domain, whatever that might look like. And we're going to try to do this same kind of stuff, and we're going to get down to the circumstance of having to talk about the size of a piece. I've got a two-dimensional domain that I've chopped up into little pieces, and we're going to have to reinterpret in that context what should size mean in a now two-dimensional context. And we'll answer that. It's not a hard question, but we'll get to that in a minute. So here's a big idea. Big picture, I'll say. Here's a two-dimensional domain. Here's how I'll chop it up into little pieces. Now in a Calc 1 class, the way you chop into little pieces is you just make a bunch of slices. But notice that doesn't cut us down into what I will call truly little pieces, right? Like that piece there, it may not be very wide, but it's pretty long. I don't think that's little enough. So let's keep chopping. And the point is just chop the other way. And now I've got a bunch of truly little pieces, right? And here's what a little piece looks like. There it is. And just like before, I'm going to take these pieces. I'm going to do whatever my calculation is, whatever application I'm interested. Maybe I'm computing mass, maybe I'm computing population, maybe I'm somehow computing work of something, whatever. Let's not worry about the specifics. But I'm going to solve the problem on that little piece. I'm going to add up over all the pieces, and I'm going to take a limit to make round-off errors go away, and we're going to declare that to be a multivariable integral on this new two-dimensional domain. Okay, so the only thing I have to adapt is, what does size mean? This is a little piece of the plane. What is size of a little piece of area? Well, area, right? I mean, it's right there in the name of it. Area is how we describe size in the plane. Other than that, everything else is the same. So here you go. We're going to have on each little piece, we're going to multiply the value of some function times the size. We're going to add up over all the pieces, and then we're going to take a limit to make round-off errors go away. There's a few details we need to talk about, but other than that, that's the big picture idea. And the notation for this thing, this is you might say a two-dimensional Riemann sum. The notation we're going to use is this. I hope it's pretty plausible looking. The idea of this notation is we use dA as a as a shorthand to represent that we're talking about little pieces of area. It's a pretty common choice. Very natural. The function that you plug into here, well, let's write that function down over here just like we did. Give me 2 seconds. And then using two integral symbols is something that's I'm not going to be able to give you a very good answer for right this moment, but that's the choice that we're going to make. Here's a bad temporary placeholder explanation. Well, it's a two-dimensional integral, so let's 2 as a visual reminder that it's two-dimensional. There's a better reason than that, but for the moment, we'll just placeholder there. And then lastly, looking at the notation for single variable integrals, there was the A and the B. What are the A and the B? Well, the A and the B are just telling you what your domain is. Right? Your domain is the interval from A to B. So A and B completely characterize the domain, but let's not lose sight of the fact that the domain is the thing that I'm chopping up. Right? The domain is really what I'm truly interested in, and A and B are just tools for helping me communicate what the domain is. Here, I'm going to indicate what the domain is just by making it a subscript, and then it's the responsibility of the writer to make sure that the reader knows somewhere else what that domain actually is. Yes, you had a question.
For domains in R3, would we be looking for like
That's a very different question. We're not gonna. Yeah. So for the moment, R2 only. Let's stick it. I mean, very natural thing to want to talk about, but that's going to be a distraction from.
Would it be like DB in that case?
It would. Yeah, but that's right. Yep. Okay. All right. So there we stop. See y'all on Friday. Real quick announcement. Let me stop the recording though.